Okay, so the final lesson in this unit on derivatives and applications is economics questions. So what we're going to look at revenue, cost, and profit, and then we're going to look at the derivative of each of these things and what do they mean, and then make some comparisons and try and learn some theory behind how this works. First of all, I think it's a good idea to just review how you would have done this in grade 10 and maybe also in 11 and 12, depending on how you were taught it, which is to think about the revenue function as a function of n, where n is the number of increases or changes to the price. So here it says the manager of a miniature golf course is planning to raise the ticket price. At the current price of $4, he gets an average of 80 customers. The manager's research suggests that if he were to increase the price by 25 cents, 4 fewer games would be played. So first of all, it's worth sort of trying to understand the shape that this graph is going to make and the reason why. So the revenue function here is going to look something like this. The revenue function is equal to the price times the sales. Okay, so the number of, that is basically the amount you charge times the number of people who pay, right? Now, both of those things depend on how many times you tinker with the price. So the price, we say, is $4, and we're thinking of increasing it by 25 cents n number of times. And then our sales is 80 sales minus 4n, because we're going to be losing 4 games for every time we make this change. Now, when you look at this function, so 4 plus 0.25x and then 80 minus 4x, what you get is a parabola which should make sense to us, because on the one side, if I raise the price so many times, eventually I'm going to lose all my customers, right? Like raise the price too high, 0 customers, right? So that would be like what's happening here at point A. On the other hand, over here, point B, or the root, right? Let's say point C. This would be the point where I have lowered the price to $0 per game. And again, it's just a model, right? So it's not a perfect representation of how many people would come if it was $0 per game. But basically, the idea would be your domain here is anywhere between -16 and 20, because those are the only legal moves you can make. You can raise the price 20 times until you've lost all your customers, or you could lower the price 16 times until you have, you're not charging anything, and therefore you're making 0 revenue. Since there are 2 ways to get 0 revenue, and they compete with each other, it stands to reason that there is a maximum somewhere in the middle of the 2 where you're looking at the ideal situation, right? So if we go the max of f between -16 and 20, it comes up with this. So the idea would be he should raise the price twice, and he will end up making $324 a day, which is slightly better than $320 he currently makes, right? So this is the idea behind a graph of this nature. So it says, anyway, determine the revenue function based on the number of price increases. So let's go ahead and expand this just so we make it a little easier to differentiate. So we have n squared, negative n squared, right? Because the 0.25 and the 4. Then we have minus 16n minus 20n, plus 20n, sorry. So minus 16n plus 20n. And then we have plus 320. So we get Rn is negative n squared plus 4n plus 320. Just expand this quickly and make sure that makes sense. Okay, so negative x squared plus 4x plus 320. Okay, so there is your revenue function. Now the derivative of this function, of course, r prime n, would be negative 2n plus 4. And what does this mean? This means how is the revenue affected by a price change, which remember is n. So what is the rate of change of revenue in terms of price changes? Okay. When is the derivative of this function equal to 0? Well, I mean, we can do this. We can go r prime of n equals 0. Therefore, 0 equals negative 2n plus 4, and n equals 2. Of course, this corresponds to the idea of the maximum, the best possible location, and we know that r of 2 is 324, which is slightly better than his current situation. So the manager should use this information to realize he can improve his revenue by raising the price twice and losing 8 games per day. 450 times 72 games a day is greater than $4 times 80 games a day. Right? That's what we basically discovered. Okay. Now, this is all well and good, and if your question is only about revenue, this is perfectly legitimate. But the thing is, this is really it's a quadratic, it's a grade 10 sort of approach to this question, and it doesn't really make a lot of sense with the rest of the concepts here. Really, we want to move to a different model where we are not using a variable that's based on number of increases. Rather, we are using a model that is based on number of items sold. Because if you think about the cost of let's go back to this golf course for a second. The cost of running the golf course has nothing to do with the number of increases to the price, right? The cost of running the golf course has to do with how many games are played. So it's a much more reasonable variable to use, would be x as the number of items as opposed to n as the number of increases. So again, the number of increases is perfectly good for maximizing revenue. It is not very good for analyzing, cost. And that's really, what I'm going to be focused on more so than revenue in this unit. So you know how to do this. It's not that hard, but I'm not really going to ask these questions. This is just a review from previous courses. Now, this time, we need to come up with a function that gives us the revenue, but instead of the variable being x, the variable is going to be, instead of the variable being n, the variable is going to be x. Now, how do you do this? To do this, you do the same thing we did above. You give a price times sales. That's the same idea we had before. Except x is equal to sales, right? Because that's what we've defined x to mean. So r of x is equal to p of x times x. P of x, of course, equals something we call the price function, or sometimes it's called, or the demand function. What does it do? P of x, the input is x, which is the number of sales. The output is P of x, which is the price to charge. Now, a little bit of a thinking question here. Is P of x an increasing or decreasing function? Explain. Okay, you should be able to explain that as we go through today. I mean, you'll get the answer in a moment, but you should be able to explain why P of x would be increasing or decreasing. So let's just go back and think about this one more time. The revenue is still the price times the sales. It's just that the sales now is not going to be a bracket 80 minus 4n. The sales is our variable, or x. The price then has to be some function that takes the number of sales and gives you back the price that you could charge to get that number of sales. And that is why you have this relationship here. The demand function is P of x, and the revenue function is x P of x. Okay, really important idea. The revenue function is x P of x. So getting the revenue is quite easy here, because it's always the same. It's just x P of x. The challenge is, how do you get the demand function, the P of x? Okay, let's look at how we would do this in the one we just did, just so we have a model. Okay, so let's go back to the golf course again. What are two things we know about the golf course? We know that P of 80 equals 4. The reason being, if I want to make 80 sales, I know I should charge $4. Now I also know that P of 76 is equal to 425, right? And I know that because if I go back up here, if I raise the price by 25 cents, I'm going to lose 4 games. Okay? Now, in our case, P of x is a linear function. Therefore, it can be written as P of x equals mx plus b. mx plus b. Okay? Now, P of x is a linear function because if you think about x P of x again, x times a linear function is going to give us a quadratic, and we know that this equation is a quadratic because we drew it. We know what it looks like. It's a quadratic, right? Now ours is going to be a little bit different than this, but it's still going to have the same shape. I'm still going to have the same quadratic shape. Now P of x is a linear function, right? And you know that P of 80 is 4 and P of 76 is 4.25. So watch what we can do. We can say 4 equals m80 plus b, and then we could say 425 equals m72 plus b, right? We could write those two statements because we're just subbing in x and y into those equations, and we know that it's linear. Now take these two equations, subtract them. Sorry, how can I do this to make it look right? Okay, if you subtract these two equations from each other, just push this over. Okay, subtract them, and what do you get? You get negative 25 cents is equal to, 4m. It shouldn't say 72. It should say 76. Apologies. 4m, and that's it, right? There's no b. So you divide that by 4, and you get negative 1 over 16 equals m. Okay, now if negative 1 over 16 is m, we go 4 equals negative 1 over 16 times 80 plus b, right? I'm just subbing in m into one of my equations. Then I get 4 equals negative 5 plus b, 9 equals b. So therefore our price equation, P of x, is equal to negative 1 over 16 x plus 9. Okay? Our revenue equation is just x times P of x, and therefore our revenue equation is just negative 1 over 16 x squared plus 9x. Now if you draw this, let's draw it. So negative 1 over 16 x squared plus 9x. Okay, now of course the graph looks different because the variable that you're using is different. However, the vertex of the graph is the same. At least a y value is, right? If we go max h between 0 and 150, you'll find that the maximum, the best possible answer is 72 sales, and you will make a revenue of $324. Okay? So vertex of the revenue function is equal to 72, 324. What does that mean? 72 is the ideal number of sales. 324 is the ideal revenue, and the ideal price is lowercase p of 72, right? We plug in 72 into our price function. So our price function's right here, remember? If I plug in 72 into that function, so negative 1 over 16 x plus 9, if I plug in 72 into that, I get the answer $4.50, 4.5. Right? So that's the ideal price to charge. So notice, we get the exact same answer in every way. We get the same price to charge, the same number of people to come, and the same revenue. The difference is our function uses x as a variable, right? And that is going to be able to communicate with the other functions in this unit. This function here will not communicate with the other functions in the unit and therefore isn't really that useful. Let's analyze this graph one more time. So let's take out the original, this one, and we'll get rid of these intercepts in this text, and we'll get rid of this demand function. Now, what can we say about this? It is possible to make 0 sales, price too high, right? So that would be what's going on over here at the origin. 0 sales, of course, means 0 revenue. Over here, you have so many sales, you had to give them away. So in other words, P of X is equal to 0. So you're charging nothing. So in order to get 150 people, or whatever this number is, 144 people to come to the golf course every day, you'd have to give it away for free, right? And again, it's like here you have 0 sales, here you have 0, you're charging nothing, and now you have, you can find your maximum in the middle. So if my company is over here, right? If my company is at point E, let's say, what should I do? Should I raise the price or should I lower the price, right? A company in point E's position is selling too few, which means they need to lower their price to sell more stuff, right? And get closer up to this vertex. A company over here, though, now is selling too much, and therefore should raise their price to sell less stuff, right? So remember, if you want to move to the right, you need to sell more stuff, which means you need to lower your price. If you want to move to the left, you need to sell less stuff, which means you need to raise your price. So one other thing we just might want to take down here for a note is that if you want to go this way, you have to lower your price to raise your sales, okay? And if you want to go the other way, okay, let's just reflect U x equals 65. Okay. If you want to go this way, you need to you need to raise your price to lower your sales. Okay. So depending on where the company is when you do your analysis of its let's say it's the derivative of its revenue, you could say, well, if the derivative of the revenue is positive, then I'm on the left side of the parabola, and I need to move to the right. I need to lower my price and raise my number of sales, right? So like here at point E, we know that R prime of E would be positive, right? It would be greater than 0, right? The derivative of revenue would be positive over here, whereas over here, let's make a point F, the derivative is negative, right? So you're going to get a question in something like, if the derivative of revenue is negative, what should the company do, right? And you would think, okay, it's negative, so I'm on the part of the parabola that's dropping, which means my sales are too high, and I need to lower my price to reduce the number. I need to raise my price to reduce the number of sales. Let's just rename this to F. Okay, so again, a lot of stuff to know about how this works, but it all makes sense, and it should all sort of fit with itself, right? So you can kind of, you can try and explain it to one another, or post question on the site if you want. Okay, now let's go back here and just analyze and understand these equations. So first function you need to understand is lowercase p of x. P of x is the demand function. Remember, input is the number of sales. Output is the price to charge. So I want to sell 1,000 objects. This function will tell me how much I should charge in order to sell 1,000 objects. The revenue function is very straightforward. You simply take your demand function and multiply it by x, and that will give you your revenue function. Okay? This is the way I want you to do these questions because, like I said, this is the calculus way of doing it. The cost function is the cost of producing your service. Now, normally this is given. Okay? Normally, like, you're going to just get this in the question. It'll tell you the cost of manufacturing or providing whatever service it is that we're working with. The profit function is a amalgamation of the two. You simply take the revenue function and subtract the cost. And here's where you realize that if you try to do this with the R of n way, you are going to run into trouble because you are going to be subtracting two equations with two different variables, and as you know from optimizing, you can't do that. You need everything to be in one variable or it doesn't work. So do not use Rn. Now, the derivative of each of these things also has a meaning, and the name of each of them is called marginal. So marginal profit is P prime, marginal revenue is R prime, marginal cost is C prime. It doesn't exactly work this way, but a good sort of way to think about what these things mean, it's like asking, what would happen if I sold just one more unit? So let's go back and look at our picture for a sec. Imagine your company F. If you sold just one more unit, you would actually be making less money. Because in order to sell that one more unit, you would need to lower the price on all your units, right? And it would actually cost you money. On the other hand, E, the marginal revenue of selling another item at E is positive, which means I should try to sell another item because I will make more money, which means I should lower my price, right?